great pleasure and honor to be here, and it's somehow surreal that you're interested in some little guy from some little country talking about some model. Well, you know, perhaps I'm from Austria. Please don't confuse Austria with Australia. There's been some issues these days, so we're not the ones with the kangaroos. It's in the heart of Europe, one of the most beautiful countries in the world, very rich in culture and nature, and also has a very important history in crystallography, what I want to tell in my talk. Once more, thank you very much. Due to my financial background, it's otherwise impossible for me to attend a congress like this one. So once more, thank you very much that it's possible to be here. First I have to tell you, you will be hearing a lot of things today, and you may think that I'm a crazy maniac doing crazy things, but I want to appeal to you that I'm, on the other hand, also a crystallographer doing some sound science, most of all on crystal chemistry related to minerals. This is just an example to give to you. It was some nice study where we found the short stone hydrogen bonds, non-mineral type compounds, but I'm not talking on this. Just please keep in mind, I'm not only crazy, but also doing science. I'm, on the one hand, scientist, on the other hand, I've dedicated my life to science communication. This is what I'm talking about today. So I want to talk to you the road to Hyderabad, how the model which is standing in the entrance came here. So I'm unfortunately not employed, I'm self-employed in science communication. This is what am I doing? I'm giving talks wherever possible to general public. I'm visiting schools and kindergartens with experiments I've created and things, different things to show. I've been creating installations for museums. I also have some touring exhibitions on my own, touring through the entire country, telling people what is a crystal, what are the properties of crystals, and most important of all, which is the relevance to our daily lives. For example, in 2009, it was the International Year of Planet Earth. Then I was honored to prepare a road show, so I prepared an entire truck to drive through the entire country, and I was standing there at all the places giving lectures to school classes with interactive displays in this truck. So this was the International Year of Planet Earth in 2009, and then came International Year of Crystallography, most important, in 2014. And then, because I'm in Austria, I'm known all over town to be so eager to talk to public and tell people what crystals are and why they are important. They told me, well, do something about that. And there was a touring exhibition which I ran through the entire country, again on what are crystals, why are they so important, tours for many, many school classes, in numbers, just to give you an impression. You may see that I didn't get much sleep in 2014. I was there all the time, touring through the entire country, giving tours for school classes. Aside from the touring exhibition, I gave 93 public lectures, visited 182 schools, and so on and so on. I did really do a lot, and this is how I got in contact with IOCR. Because I did also some other things, like for example, I designed the official stamp, the Austrian stamp. There were a lot of stamps on crystallography in 2014, which were recorded on the IOCR homepage. And here you can see this picture was provided by Michele Seema, thank you very much. And here right in the middle, that's the Austrian stamp showing crystallographer Felix Achatschke, whom I will address later on. So, and this is what some colleague of mine did. Son Bragg. So I told this, and this is from a talk of Michele, which he gave in Rabat in Morocco, which was on the Crystallography Matters More assembly, where
And this was the last slide of his presentation, connecting to actions after the year. And I was very proud that this was the last slide he showed, announcing that I was trying to set a world record to build this large crystal structure model. So this is when it all started. It's now about materials and methods. To build such a large crystal structure model, you've really got to have the balls. So I've been looking for balls all over the year, and it was really difficult because there were none on the market, so I have to specially produce them. And I did a lot of experience on materials, and in the end, we found a very good solution of balls which are very robust and most of all, very, very accurate. You have to be very, very accurate in building such a large model, because a variance of 1 millimeter is far too much, or in angles 0.1 degree, you soon get a huge problem. It doesn't fit anymore after a few translations. So this took several years of preparation, and finally in 2015 I could start assembling, and this is what I did in 2015. It took over 400 tubes of glue, super glue. There's also many tests about this. This is how my flat looked like, by the way. So this is where I live. My bed used to be somewhere back there. But the entire flat, from bottom to top, was filled with atoms. Even the bathroom, everything filled. In the end, there was only a space, 1 square meter, where I slept. This is exactly the place where I slept, yes. And I was finally, so I built the model in modules, which just fitted through the door. And then there was an atomic transport to the site where I assembled all these modules, which I was honored to assemble in the courtyard of the City Hall of Vienna. So this is the City Hall, back there is the backyard, this is the site where I started, this is the very first day, the first module put there, and it was there in public space. I think it's very important that people see what we are doing. And there was, right from the beginning, a lot of school classes and kindergarten groups visiting the model, and general public, in the end, from over 50 countries visited the site. I was lying there on the floor all the time, which was very inconvenient, or being upstairs. There were even larger ladders, being somewhere in 3 meters height, building the model, and in the end, I finally made it. So this was the finished model in 2015, which consisted of 38,880 balls. Connecting sticks, when you put them next to each other, is more than 12 kilometers of sticks in there. 400 tubes of super glue, a cube about 3 times 3 times 3 meters, and it was in the end really registered by Guinness Book of Records and also by Rekordinstitut für Deutschland, which is the German equivalent, as a world record. It is the largest crystal structure model in the world. So this is the certificate, and what you can see on the picture, I'm very glad that it's finished and no more balls in my room. And another thing is, this is also something I wanted to show. The periodicity, how does it look like with the naked eye? You walk around the model, you can see it also on the model here, and with every step you take, in each direction you look, there are different patterns, there are stars, and it's really, really fun to look at it and to take pictures from the different directions. You can do it yourself here, just to give you a few impressions. You can really HKL what you like, look for the symmetry axes and planes. In every direction you take pictures, it looks different, twofold axis. I prefer the threefold axis. These are very nice, but you can try yourself outside. It even looks different when viewed through the camera than with the naked eye. It also looks very nice in transmitted light, so these were in reflected light, this is in transmitted light, giving also very nice effects. And I think in the entrance hall, it even looks better in transmitted light, like at that picture. So why did I do this? To communicate crystallography to general public, most of all to school children and kindergarten groups. I gave a lot of lectures there on crystals and to visitors from over 50 countries. This is the youngest visitor, I guess. And what you can see here is that the balls are really, really robust, and you can also touch them. They can be, it was outside, so the weather was also no problem. At the display site at Vienna, there was also some other nice possibility. There was a big screen, which is not here today, but it is in Austria, because you can put a virtual graffiti on any ball of the model, so you can sponsor the ball. The entire project was funded by myself, and I had to try to refund it a little bit. And so you can sponsor any ball, and this is just an example. You get also a certificate by doing so. When you look at the homepage, this is the last one entered, which was from a crystallographer as a present for some colleagues, crystallographers, who just had their wedding a few days ago in Hyderabad. So if you're looking for a nice present, please visit for the homepage. So, oh, that's interesting. Okay, you probably have also seen the big billboard where we just took the photos of the stamps, the Austrian and the Indian stamp of International Year. And there's a famous quote of Ernest Rutherford, who said, "All science is either physics or stamp collecting." Well, probably that's a reference to his saying. But it was really interesting to connect crystallography and philately in this respect. So we'll continue somehow philatelic to the end of the talk. In 2015 was not only 100 years of Nobel Prize of the Braggs, but only 175 years of postage stamps existing. And therefore there was also, on the occasion of the crystal structure model, and a separate Austrian stamp issued on this topic, which you can see on the billboard outside, and it was emitted at the display site with special stamps and special envelopes, which were also given out at the special occasions. And this is the most important thing, why I built this model, as a platform to celebrate milestones of science history. Because in the end of 2015, when I built the models, it was exactly 120 years ago that Wilhelm Conrad Röntgen started his studies, which culminated in his famous discovery of X-rays, which by then was by chance exactly 150 years ago. Exactly 100 years ago, when I was there standing with the model, Nobel Prize was decided to be given to Max von Laue for his discovery of diffraction of X-rays on crystals, proving that they are arranged, that atoms are arranged in a periodic manner in crystals. So he received the Nobel Prize in 1914, which was decided in 1915. And in 1915, the Nobel Prize was awarded to William Henry and William Lawrence Bragg, but there will be an own separate, very good talk by Mike Glaser afterwards on this topic, but this was most important to me, to celebrate this famous milestone in the history of our science. With a special celebration on this occasion, there were members of the British and German embassy, which I think is very important because exactly 100 years ago, William Lawrence Bragg was engaged in World War I, and Germany and Great Britain were enemies back then. 100 years later, we're now, let's say, brothers in science. And we also had a special drink on the occasion. We had the same type of wine as William Lawrence Bragg drank when he heard about receiving the Nobel Prize. So I'm very keen on, on wine. I'm very interested in the topic. By the way, there seems to be another world record I hold. I seem to have the largest collection of wines named after crystals. And probably some of you have met me at the International Mineralogical Association meeting in Budapest, where I showed over 100 bottles named after crystals and gave a wine tasting. So probably if someone's doing some event like this in the future, please just ask me. I'm doing this professionally and I have a degree in wine tasting. So back to history of crystallography. Bragg taught us how to determine the crystal structures, and especially there were Austrian students which got very involved in this topic. You for sure know Max Perutz, who initially came from Austria, was a pupil of Bragg and got the Nobel Prize for determining the structure of hemoglobin and other substances. And on the inorganic side, on the mineralogical side, there was Felix Machatzky, who was honored on this stamp, which I just showed you, which was the Austrian stamp for the International Year of Crystallography. He, by the way, was the first to postulate the crystal structure of feldspars, or silicates in general, which are the most abundant substances in the Earth's crust. So even in Austria, hardly anyone knows that it was an Austrian discovery, in fact, in the 20s. And I was giving a talk in International Year of Crystallography at his birthday in the house where he was born in Styria. And in 2015, when you look at these dates, there were also round anniversaries of this very important person in the history of crystallography. In the end, when there was the celebration of the world record, it was an honor to welcome Mike Glaser in Vienna and to celebrate the end of this project. But back then, we began to talk, what's about Hyderabad? Isn't it possible to get the model there? And it was not that easy because I had to disassemble the model because it never was meant to fit into a container. So I had to disassemble it, rotate it by 90 degrees, build some transportation box. This was a lot of work, but finally it worked and it was put into a container. And in June, we started shipping it to India, and I think it arrived last week. So it finally turned out to be fine. So what are the conclusions? Please visit the model in the entrance room, have a lot of fun taking pictures, looking for symmetries. It's really fun. I will be standing there all the time answering questions and giving hints which positions are good for taking pictures. If you like to display the model yourself, so it can be disassembled to modules and even small parts look really good, and they've been shown, at least in Austria, at several places. There's a small part, for example, which was shown in Leoben at an exhibition on natural resources. So if someone's interested in displaying the model, small parts, or the entire one, please get in touch with me. You will see my contact details at the end. And the last thing to tell, this is completely new. If you like to build some model like this, perhaps a smaller one, yourself, it's now possible. Because I've gained so much experience in building such large models with materials and so on, and I saw that there is worldwide no product to build such crystal structures. I've now began to produce them myself, some more balls, which are very robust, easy to handle, and very, very accurate, which can be used for education of crystallography. I've developed a special ball, I call it the universal ball, which can be used to build over 15 different crystal structures, representing more than 15,000 compounds. So it's an offer. You can use this for crystallographic education. And what we just heard is that the next IOCR meeting will be held in Prague, which is right next door to Vienna. This is also an official offer. I don't know if someone of Prague is here at the moment. We could ship easily the entire model there, the big one. So this is only a small part which is visible here. And another offer, by then we have these balls, we could also altogether assemble a new model. Not only sodium chloride, but perhaps something more difficult like perovskite. It's no problem. We can assemble any model with these balls now. Just an offer, we can talk this over. If you're interested in these educational kits or these balls, please visit my homepage, get in touch with me. The homepage is given at the very end of this talk. Probably the next opportunity to see the model is the ECM meeting, which will be held 2019 in my hometown in Vienna, but there's also a separate stall in the exhibition area on that topic. So I'm finishing, hopefully in time. I want to say one more time, thank you very much for making possible to be here. The meeting committee, the Indian Institute of Science, most of all IOCR, INSERB, I thank the University of Vienna and Austrian Cultural Forum, by name especially Professor Desi Raju. Thank you very much for making all this possible. I also thank Professor Marvin Heckert from IOCR, the members of the local and the international committee, Carola Smith and Christina Ginovic-Carugo from University of Vienna, Michele Sema and Mike Glaser of IOCR for making all this possible. And in the end, I thank you very much for your attention. Are there perhaps any questions?
Just a curiosity, when you had to make the holes in those balls, and since, as you mentioned, they will be extending far beyond, and even a small deviation, did you use any special instrument to find the location of those holes on every sphere? Or how did you do it so accurately so that, you know, the extension all linear and orthogonal? You comment on that?
This is a long answer. Perhaps we'll talk this over afterwards. But to make it short, we did a lot of experiments on this, and this was really hard. And some of them were, most of them were pressed. But now I have a special device for drilling them very accurately. So there's a special device to rotate it and to drill it, which was kind of hard to find out, but in the end it worked.
I've already been asked by someone whether one could build a model of the diamond crystal structure. And obviously it can, from something like this. I'm sure they will be, yes.
We can build any crystal structure from now on, even if it's some very obscure, I don't know, not only simple compounds, but any can be produced on demand.
Molecular crystals would be slightly more challenging, I think. But I'm sure most of the extended inorganic solids could be handled quite easily with those, with the choices that he has mentioned. Any other questions? Please.
We use 3D printing actually to make similar thing that you are showing it, not exactly the same, but our experience is that you know, even to extend it by 4 or 5 atoms in a row, it was collapsing. So that
unfortunately this doesn't work, and it takes 3D printing takes far too much time.
So print 40,000 balls takes some time. And at the moment it's not as accurate as needed. Yeah.
You see, one appreciates immediately Robert's comment that in making the balls, even for this structure, the tolerance in the angle is what, a few minutes? Or few minutes, or in the case, degree, yeah, a few minutes, seconds, yes, and seconds. And in the case of the distances, themselves, again, very, very fine tolerance. Otherwise, you will not, human eye can detect extremely easily any distortions in these things. And I was looking at that model yesterday quietly in the morning, and you cannot see any distortion. At least I couldn't with the human eyesight. So which means that the degree of angular and distance control that he has obtained in the model must be very, very high to get a model of this type. Yes, indeed. Yes. Any other questions, please, and comments? For the sheer novelty of this idea, I mean, we've had crystal structure models which we use in the classroom. They've been going on for more than a century, little things. But it's the periodicity that I find it is so amazing, and you're able to discern in the simplest of structures all sorts of things. And many of the physically oriented crystallographers have been asking me about defected crystals, dislocations. These things, I'm sure the educational value of making models of this type, it wouldn't come within the 59 structure types that you've mentioned, but if, for example, you could show an edge dislocation, something like this would be really, really super, yes, because then you get a concept even of things like solid state reactivity and all, which is completely novel and quite true and real. The thing about this model is that it's real, and this is what I found personally the most amazing thing about this structure. Yes, please, Michele.
First of all, I want to thank you again, because we've been in contact so many times, and you really make the International Year of Crystallography different and much better because of all the activities you did, and because of your great capability in engaging people, which is the main thing. So I very much look forward to seeing your next project, and I don't want to ask you what it will be. But my question, since all the questions here are about crystallography, and I'm interested in the engagement activities and in communication activities that you have done. So what kind of people were attracted by this model? You have talked with students, you have talked with senior people, general public. What kind of activities have you done around the model, and what you think will be useful to do?
You mean on the model in special? There were, which people were there? So from kindergarten, small kindergarten, you saw the small guy over there, up to very old people, so anyone interested, and I've been contacting the kindergarten groups and schools, so this is very important to outreach, to talk to the people, because all of them think crystals are but glittering stones, and I think it's most important to tell people what crystals really are and why they are relevant to our daily lives. This is what I committed my life to, dedicated my life to, and therefore I undertook this project, and it was really nice to see that there were a lot of people coming to Vienna. I had visitors from over 50 countries, and once there was a couple from South Africa, I think, who said they read about the crystal model in the newspaper, which I never thought to be possible, and this is why they took a ride to the city hall to visit it. Well, this is again here. It's for me it's somehow surreal, and I'm very, very thankful and honored to that I can do something about communicating crystallography.
Thank you so much, Robert, for the talk, and also for sharing a few days with us here in Hyderabad. Thank you all. We move to the next talk now, which again deals with sodium chloride, but in an entirely different way. It is my pleasure to introduce to you Dr. Dinkar Joshi from Bombay, and he is an expert on Mahatma Gandhi. What is the connection here between Gandhi and common salt? This is, of course, the answer is clear to all Indians, but I don't think many foreigners know the connection, because in 1930 Gandhi organized what we call the Salt March or the Dandi March, when he took a group of volunteers to the beach on the Gujarat shoreline in Western India and picked up a handful of sea salt. Now, what was the significance of this was that, this all of us know, is that salt in those days was taxed by the British. And so when he picked up the sea salt, he was telling the British, in other words, that he was not interested in paying the tax. Now, this is known to all of us, but I do believe Dr. Joshi knows a lot more about this topic, because he has dedicated his life to a study of Mahatma Gandhi. His background is that he was a bank officer for many years, and he has written extensively in Gujarati, but also in English. And very recently, he wrote a very controversial and acclaimed book called Mahatma versus Gandhi. And if you know what this signifies, Gandhi's eldest son, Harilal, was a person. Gandhi had 4 sons, and the eldest son and Gandhi were on very poor terms throughout their lives. And so Mahatma is, of course, Mahatma Gandhi, and the Gandhi is Harilal Gandhi. So that is the title of the book. And it's a long story, but I'm sure he will tell this and many more. Dr. Joshi, it's a great pleasure to have you here today.
My Jai Sri Krishna to all, and good morning to each one of you. Frankly speaking, I should be odd man out from this galaxy. And Professor Gautam Desiraj in particular, he invited me to speak on Dandi March, on Salt Satyagraha, and as such, I am here to talk to you. Actually, he has rightly told that I am a man of letters, of Indian history and culture. All this technical side of crystallography is like a Latin and Greek for me, I must confess. But the salt satyagraha, the salt, the basic element, all of you are studying the basic element salt, and Gandhi has picked up that salt. Now those who knows Indian history, they know what was salt satyagraha. But the man, our guests from foreign, they have come over here, they must not be knowing much about that. In our Indian folk literature, salt is known as Ram Rasa. Salt, the other word. Salt is known as Ram Rasa. Ras means taste. Anything is tasty, then we find rasa in India. And if in a dish served to you on the dining table, beautiful items are there, number of beautiful items are there, which you like, but there is no salt in all these items. Would you like it? You cannot eat it. So without a small quantity of salt, all this beautiful dish is of no use. Similarly, the life is of no use if there is no God, no Lord, no Ram, without Ram there is no Ras. And that is why salt is known as Ram Ras. Probably Amitabh Das must be knowing, in our side Gujarat, salt is known as Ram Ras in folk literature. Now, you must be knowing that a man, a handsome man, or a beautiful woman, very nicely dressed, educated, from a very decent family, and in his or her body, iron, phosphorus, salt, every item, chemicals are there. But suppose salt is reduced, then what will happen? That beautiful lady or a handsome man will be imbalanced immediately. He will start talking irrelevantly. And that is why in our side, the man without common sense, without understanding, is known without salt. Without salt, a man is there, then he is without common sense. That is the importance of salt, that I want to say. Now, what has happened in India? The freedom movement from 1857 to 1947, 90 years. The first mutiny, they say, or we say first freedom movement in 1857 was failed. And thereafter, everything was going on for freedom. Britishers came in this country in the 16th century, 17th century. But in the 18th, they had come over here for trade only trade, nothing else. But when they observed, British East India Company, when they observed there is an opportunity to seize the land also, to rule also, there were opportunities, lot of opportunities for them. So they took that. And in Bengal, in 17th century, in the latter part, Robert Clive first captured the land, 24 parganas. 24 parganas was the area which was ruled by the British first time in the latter part of 17th century. Now what happened at that time? From Calcutta to Liverpool, daily one ship was transmitting. A daily one ship with Indian goods, which was very costly in England and Europe. They exported from here Indian ship daily from Kolkata to Liverpool. And Acharya Kripalani subsequently in 20th century calculated all these things. And he has written that one ship meant 1 lakh of rupees in those days. In those days, 1 lakh of Indian rupees were shifted, were transferred from Calcutta to Liverpool for 365 days. Now you can calculate. When the ships were coming back from Liverpool, they were empty. So during the journey, what had happened? Ships could not be balanced because of the sea, because of this tides. Ships were imbalanced. So what the Britishers they did, while coming back from Liverpool, a few bags of salt, because salt is heavy, when it is wet it is more heavy, the few bags of salt, they were impounded in the ship to balance the ships. And this Liverpool salt were dumped here at Calcutta for years together. Now there was a mountain of ships, Liverpool ships. What to do with this? So the British ruler, by that time, this 24 parganas rule was extended in many parts of the country, British rule. So what they did, they were trading community, they were trading community. So this Liverpool salt should not be wasted. How it can be sold in the Indian market? There was only one way, that if Indian salt is costlier, then Liverpool salt can be sold. And that is why, first time in 1765, salt was taxed. Salt was sold to the ठेकेदार. What we say is ठेकेदार, license holder. Some license holder were contractors, were sold the area, and that is why Indian salt became costlier and the Liverpool salt became cheaper, and in the market Liverpool salt was sold. That was the basic idea. With the result, what had happened? Within 5 years of time, 3.52 months, 3.52 months was our measurement, 82 kilograms, 82 shares, 40 kilograms. That was the measurement. Was imported from Liverpool to Calcutta. Within 10 years' time, it was 18.52 lakhs. 5 times, 6 times. And with this, Indian salt was costlier in India itself. Now friends, in 1929, in Lahore, on the bank of Ravi River, a Purna Swaraj resolution was passed by the Congress, Indian National Congress. Purna Swaraj, full freedom for the country, which was a challenge to the British government. And Gandhiji was appointed as a dictator of this movement. So what Gandhiji did, first time he wrote a letter to the British Prime Minister Ramsay MacDonald. British Prime Minister Ramsay MacDonald, he wrote a letter. In that letter, Gandhiji narrated that if the following 11 items or following 11 issues are not taken up by the Britishers in time, I will have to start a movement. Now in these 11 items, salt was one of the items. Reducing of military expenses was another item in Purna Swaraj. Prohibition was also one of the items. Throughout the country, in India, prohibition should be there. Now Ramsay MacDonald did not reply of this letter. So Gandhiji wrote another letter to the Viceroy, Lord Irving, in which it is stated that if nothing is done, I will start my Satyagraha against your Salt Act. Now, why did he prefer salt? Now, as we know, that salt is the item which touches to everybody's life, from top to bottom. If one is staying there, Mr. Bill Gates is there, then the last man of India, everyone has relation with salt. So Gandhi preferred salt, and he wrote to the Viceroy that I will start my Satyagraha on 12th of March 1930. Now why did he prefer Dandi? Dandi is a small place, 241 miles away, miles, not kilometers, 241 miles away from Ahmedabad. Gandhi's Satyagraha Ashram, Sabarmati Ashram, was at Ahmedabad. And Gandhi assigned this job to Sardar Vallabhbhai Patel. Sardar Patel was very familiar with this area. Earlier, he has taken up many satyagrahas, conflicts against the government in this area. Bardoli Satyagraha, Kaira Satyagraha. Sardar Patel was the leader. So he was knowing. each one, each village, and Dandi also. Dandi was a small place. Dandi is still there. Dandi is a small place on the coastal area of Gujarat. So Gandhiji started his Satyagraha movement on 12th March with 78 participants. 78 participants. Out of these 78, Gandhi was the eldest one, 61. And his grandson, Kanti, was the youngest one, 16. Gandhi himself, his son Manilal, second son, Manilal, and grandson, Kanti, 3 generations were there in that procession. Apart from that, other total 78 participants were there. No ladies were allowed. No ladies were allowed. When some ladies approached to Gandhiji, ladies were there in Satyagraha movement, in freedom fight, but why not in this Satyagraha? Then Gandhiji has replied this way, that when Mughals and Muslims, they were attacking this country, then Hindu princely states were there. So Hindu princely states, when opposed against this Muslim invasion, the Muslims invaders, they know that Hindus, they respect Gandhi, they respect cows like mother. So what these invaders did, they collected cows. They kept their cows in front of their army. So Hindu's army cannot attack when cows are there. And Muslim army men, they can attack. That was the intention. So Gandhiji told at that time, if we keep ladies in the procession, in Dandi March, then what will happen? British policemen will not attack us, because ladies are there in front of the procession. So Britishers, Gandhiji knows, they will not fire, they will not arrest, they will not do anything. And so we cannot take protection this way. So Gandhi did not allow ladies. And the procession started from 12th March 1930 to break the law. Gandhiji wanted there should be no tax on salt. He gave 3 types of satyagraha. One, let us go to Dandi. He asked all Indians that whenever sea coast is available, every one of you should go there and pick up the salt. Pick up the salt. Manufacture the salt there. Those who are not on the sea coast, they should possess the salt. Whatever salt is there, they should possess. Third type, they should sell. They should sell the salt. Now a handful of salt was sold for hundreds and thousands of rupees in those days. When 241 miles from Sabarmati Ashram to Dandi within 25 days. Everybody was carrying their own beddings. And at night, when the village comes, they will take night out there. And people from that village will serve them dinner. And that dinner was only chapatis, khichdi, sabzi, something, and a glass of milk or curds. That was the system. Everybody has to carry his own bedding. This way, these 78 people, for 25 days, march was continued, and 5th of March, 6th of March, 6th of April, they reached at Dandi. And at Dandi, Gandhiji in the morning at 6:30 picked up handful of salt. Now in this Dandi march, there was one horse also. Chinubhai Baronet of Ahmedabad provided one horse in this Dandi march, with the reason that if Gandhiji could not go ahead, he was 61, then sometime he can ride on this horse. But Gandhiji refused. In between the Dandi and the Sabarmati ashram, when he noticed this, he asked Chindubai Baronet to take this horse away. This way, they reached at Dandi. Now, in one of the villages, when night halt was there, that village asked for some milk quota from the nearby town for all 78 people, participants. When Gandhiji knew it, he got annoyed. He told them that we are not here to get reception from anybody. We are here to free our country, and this is the march for freedom movement. So nobody should do like this. No milk should be taken from outside. If you have, you serve us. If not, don't bring it. That Gandhiji insisted. Meanwhile, in one of the villages, Gandhiji told, a vow was taken. I will die as a dog or crow, but I will not come back without Swaraj, without freedom. And that was very known to everybody. Everybody, in the procession, they told Gandhiji, and Gandhiji insisted, I will not come back to Sabarmati ashram unless freedom is got. So this Sabarmati, this Dandi March is a very important chapter of Indian freedom history. With this, 1931, civil disobedience started, and with the result of this civil disobedience, round table conferences at England took place, round table conference, and with this, 1935, Government of India Act was passed, and in 1937, autonomy, provincial autonomy was obtained. This way, this is the very important chapter in Indian history, where salt, the basic element, has played very, very important role this way towards the Indian freedom. One thing I would like to tell, even today, salt is taxed. After 70 years of freedom, salt is yet taxed. In 1962, when Morarji Desai was the finance minister, a resolution was placed in the parliament to do something about this, but nothing was done at that time. Until today, taxes are there. While going through the history, it seems that even in Mauryan age, when Chandragupta Maurya was there, Chanakya has written Arthashastra, in which a list of taxable items is given, then salt is there. Salt is a taxable item during the days of Chanakya also. In Muslim rule, in 14th, 15th, 16th century, salt was taxed 5%, those who are manufacturing, they are Hindus, and 2.5%, 2.5% for Muslims. That was there. So salt is always a taxable item also, for which we fought. I am thankful to each of one of you for giving me patience. Hearing or listening, I do not know, but I hope you must have given me listening. I thank you very much once again. Either everybody is very clear what I said, or nobody is understood. Thank you.
right, of course, is a PhD student of Kathleen Lonsdale, who herself was a student of W.H. Bragg. So his academic genealogy goes right back to the starting point of our subject. I have great pleasure in inviting Mike to give his talk on the Bragg scientific school.
I'll try and do this without a microphone. Can everybody hear? Yeah, good. So, what I want to do is to take you back just over 100 years to how science was at that time. X-rays had been discovered 4 years earlier, and I want to convey to you the idea of how little really was known about X-rays. I think I can do that. I hope. There's a long history here, and the slide I'm showing you just shows you a few examples of salt in different forms, postage stamps, mines, crystals, and so on. But in 1912, at that time, there was a lot of discussion going on in physics as to what was the nature of X-rays. The big question at that time was, X-rays, are they particles or are they waves? And they couldn't solve the problem. A lot of experiments were done since the discovery of X-rays in 1895, right up to 1912, and even attempts at seeing what happens when you put a crystal in a beam of X-rays. They never discovered anything in the way of crystallography or anything that followed. So, if we have the next slide. This talk is mainly about two very famous scientists, father and son, William Henry Bragg and William Lawrence Bragg. One of the problems in this area of science, when you try to study it, is everybody is called William. That makes life very difficult. Father and son, as we all know, shared the Nobel Prize in 1915 for their discovery, essentially of X-ray crystallography. And it's that discovery really is the reason why we are here today, many years later. It's the reason why we know so much about the structures of solid materials, ranging from metals, inorganic materials, organic materials, pharmaceuticals, proteins, viruses, DNA, genetics, all these things come from this initial work of the two. So I want to take you back to those times a bit to see what was known and how did they go about starting this subject off. Now, the first bit of work was done in Germany in the early part of 1912 by Max Lauer, who was what he became Max von Lauer later on. At that time he was just Max Lauer, and he was working in the Institute of Theoretical Physics in Munich as a private docent with the great physicist Sommerfeld. And in Sommerfeld's department at that time, the keen interest was this question: what are X-rays? It was Lauer who got the idea of using crystals with an X-ray beam, because it was known that crystals, we suggested, I should say, that crystals have a periodic arrangement of atoms or molecules, change his story a few times in history. So it's not entirely clear exactly what happened. But very quickly, Sommerfeld, Lauer had this idea of doing an experiment with X-rays and crystals. Sommerfeld didn't want him to do it, didn't want to spare any resources. So there was a kind of, I wouldn't say an argument, but a disagreement between Lauer and Sommerfeld. At that time, Röntgen had moved to Munich and had a lab with an X-ray set. And it is said that Lauer persuaded two people, Friedrich and Knipping, one was a student at Bredton, one was an assistant to Sonnenfeld, to try out the experiment in secret. In fact, Ewald once told me that they actually stole Bredton's equipment. Here's this. It's not sure whether that is really true. That's what he said. Anyway, in April of 1912, they carried out the experiment on copper sulfate, copper atoms. And the reason for this was that Lauer had the idea that the diffraction, if it occurred, would come from secondary X-rays emitted by the copper atoms. And if these X-rays coming out of the crystals would give us some sort of pattern. The mistake, the area, his assumption here was wrong. And nevertheless, this is why they tried copper sulfate. And the diagram in the middle is the famous first photograph found after a lot of effort. And it's not a very nice photograph, but you can see the X-rays in the centre have been deviated somewhat. And very soon, they tried zinc sulfide, and they've got this pattern here, and what you see now is spots. And you see the spots are arranged in a symmetric pattern. So you see for the first time symmetry, which is at the heart of crystals, and the X-ray pattern, the diffraction pattern they get, is just shows the same effect, suggesting that you really are getting diffraction, that it's really telling you something about the arrangement of the atoms in the crystal. And Lauer and Friedrich and Knipping, they put together a paper to explain this, and Lauer came up with some equations, perfectly correct and not very useful, to explain it. But he couldn't explain all these spots. He could explain some of them. One of his problems was he assumed that the X-rays, because he was thinking of this secondary radiation, was just a single wavelength. And then later on he thought, well, maybe there are 5 wavelengths or something. He couldn't get that to work. And it was the young Bragg, just qualified in Cambridge, 22 years old, working with his father, who came up with a solution. Now his father believed X-rays were particles. And at first the two of them were doing experiments together to prove that. And they heard about Lauer's experiment from a colleague, Lars Vegard, who sent them a letter, and that intrigued them, and they tried some experiments to prove actually it was not diffraction of waves, but it was particles coming through channels. The experiments failed. And it was young Lawrence Bragg, back in Cambridge, walking around, suddenly had an idea. He realized that if you look at this pattern, oops, go back, sorry. Look at this pattern, then if you look at these spots, they're elliptically shaped. And if you look at the ones on the top and bottom here, as you move the photographic plate away from the crystal, they become more elliptical. And that suggested some sort of reflection from planes. That's what you get. And that was his first idea, that really we can treat this as reflection of some sort. And then when you combine that, allowing the waves, or the radiation to interfere with itself, if it's waves, you get an interference pattern. And this is from his notebook in 1912, and I hope you can see here at the top, 2D cosine theta. That is the first evidence of Bragg's law. 2D cosine theta. It's not in the form we use it today. And this is because Lawrence Bragg was well versed in optics. And in optics, when you have a light beam refracted through a crystal, we think in terms of the angle of incidence. So this is the first evidence of this concept. Lawrence Bragg then wrote this up for publication. It was presented on November the 11th, 4:30 in the afternoon, to the Cambridge Philosophical Society, which was based in the Cavendish Laboratory, Cambridge. The paper was read by J.J. Thomson, not by Bragg, because Bragg wasn't a member. And you can see here on the left the original notes that were taken at the time of that occasion. So that was read in 1912, November the 11th, and then it was printed up for the Cambridge Philosophical Society, On the right-hand side, you see the first print. This is actually Lawrence Bragg's personal reprint here, and it's dated in 1913. And there's always been a controversy in the literature as to what year this famous paper took place. Was it 1912, 1913? And even Bragg got it mixed up sometimes. So, what was the significance of it? Well, I said it was J.J. Thomson, who was a friend of Bragg at that time, who was in the department, who read this paper. J.J. Thomson, Nobel Prize winner, discovery of the electron, and he presented this paper, and on the right-hand side, it's difficult to read, but this is the first page of that, and the title of this paper is The Diffraction of Short Electromagnetic Waves by a Crystal. He doesn't mention X-rays, because he didn't want to upset his father at the time. But his father was a great scientist, and very soon realized the importance of what his son had done. And he, W.H. Bragg, started to publish notes in Nature, pointing out what his son had done. Very proud of what his son had done. So the paper appeared in print in 1913 in its cosine form. So it looked like that, lambda equals 2d cosine theta. Why did it become sine theta? Well, that's because the father, W.H. Bragg, invented a device called the ionization spectrometer, which is the beginning of what we call the diffractometer. And I believe the reason that it was changed is when you use a spectrometer, you measure from the incident beam direction out to higher angle. And so it is natural to use not the angle of incidence, but the angle of reflection, which is 90 degrees minus. There's no print of this, but that is my belief is what they did. So came 2d sine theta. And it became very evident to Bragg, to the young Bragg, that the X-rays that were being used were being scattered over the incident X-rays, and that the X-rays were not a single wavelet, but were a continuum, a white beam of X-rays. And you can see from the Bragg's formula, there are three quantities: wavelength, despacing, angle, and you only get that equation obeyed if all three quantities fit it. So the idea is that you may have a white beam of X-rays, but the crystal selects out those wavelengths from that satisfy that equation, the particular orientation of the crystal. I have to say that Lau at first didn't understand this. He believed that if you had a continuum of X-rays, the film would be fogged. So it took a little while for him to appreciate it. Now Bragg had all the advantages going in his way. In Cambridge, he was in touch with various people who were working on crystals. He began to learn what crystals were. Lowry was unfortunate that he was in a theoretical physics department. People didn't really know much about crystals. And Lowry himself, as he admitted, he'd fallen asleep in the lectures on crystals. So he hadn't appreciated quite exactly what a crystal was. And one of the mistakes that Lowry made was, in trying to interpret the zinc sulfide structure, was he took a cube and he put the zinc sulfide on the corners of the cube as what we would call a simple cubic type of arrangement. And because of that, he couldn't understand the pattern. So this young man, at 22, has seen through all of this work and produced the most important discovery of the time. Not bad. Okay, so we go on to what happened with salt. And what's going on there. So now in 1913, the subject of X-rays and what you do with crystals now reside almost entirely with the two Braggs. They had the field to themselves. And one of the confusing and difficult things when you look back at this is they were publishing loads and loads of papers, almost simultaneously. And many of these papers are saying the same thing, sometimes little differences. They seem to have the whole of the publishing field to themselves. It is evident when I look at the papers that there was no refereeing going on, there was no editing going on, they just were producing stuff in a rather unique position. On the left-hand side, I've given you a few of the references, and the top one is the first one, the two of them father and son published together. This is one of the papers which describe the ionization spectrometer, and in which we first see n lambda equals 2d sine theta, what we now call Bragg's law. So it appears there without comment, but it's clearly being used. The second paper here is the paper they usually refer to as being the first paper on sodium chloride. Actually, sodium chloride was discussed even in this paper, and in that paper they had suggested that the unit cell of sodium chloride would contain 4 sodium chloride molecules. So they were already, at this point, thinking about that structure. But it was the next paper, this one here, here's the front cover of that one, the structure of some crystals as indicated by their diffraction of X-ray. X-rays now appears in the title, and it's this paper which one has to look at to understand what they did, or what Lawrence Bragg did, in fact, to get at that structure. So I want to just say a few words about that. The paper is quite difficult to read by today's standard. The language is a little different, and it's actually not a very good paper. It's has a number of inconsistencies and errors in it, which you might not have expected. But the young Bragg, he was in a hurry. He still had a lot to learn about how you publish things. His father was much more controlled and much more. He was the famous scientist. Lawrence Bragg was not. He was unknown. But his father was the famous scientist of his time. Well-established fellow of the Royal Society, highly respected, and a character who very self-controlled, very kind, very gentle, very shy man, but not given to emotion of any kind. And that sometimes he appeared to be rather stiff to people. But actually he was a very, very nice person, a very open person. And in fact, let me just make a point here that he set up research in crystallography. He had a lot of students. In fact, he had 18 research students in his time. And uniquely, at that time, 11 out of the 18 students were women. If you think about when we're talking, this is quite something. The Braggs were very open to inviting people to study crystallography with them. So, but Lawrence Bragg was different. Lawrence Bragg was emotional. He had suffered from depression, quite a different character. And there were some problems later on because the father was the person who was so well known in science. He was getting all the honours, and Lawrence Bragg was being ignored. And so it did cause a little friction between the father and son. But to be fair, the father always, in his papers, referred to his son. You can read the notes in Nature and so on where he said, "My boy did this, and my boy did that." He tried to convince the scientific world that it was his son who was responsible for the primary work. But the scientific establishment always honoured the father. And that was a problem in the family. Okay, so this is one of the first figure in this paper, and he's trying to explain these Laue patterns where you see spots occurring on ellipses. And I can show you this because it's quite instructive. So this is, at the top here is the photographic plate. This is the X-ray beam. The crystal he puts here, and he draws a circle around it like that. And here is a beam going out to the plate. And he realizes that when you look at these ellipses, they come from zones of planes in the crystal. He'd learned enough crystallography to realize there wasn't stuff with zones, which the mineralogists had invented. And so this is the center of the zone, and then you get beams going out, other indices of the zones, and so you see A to S. If you think about that in 2 dimensions, you get a ring, which when you project onto film becomes an ellipse of spots. And so these ellipses of spots were in some way connected as a zone. They were related to one another. In fact, this is very closely the same construction in a way as the Ewald sphere construction. there it is in Bragg's first major paper here. This is potassium chloride on the left. This is from a photograph that Bragg took using the Lowy method. And so the dark spots represent the intensities of the spots that he got. And you can see, well, I can see at any rate, he has put indices against each of these spots. He's learnt at this point about Miller indices, which he didn't know before. And by very carefully looking at the distribution, using that picture that I just showed you, he was able to realize that if you go around the ring, there's a zone, so you can index each of these points coming from different planes, which have a common factor in them. And what he noticed was, this is potassium chloride, same structure as sodium chloride, that just about every crossing point there was a reflection. And on the right hand side is a table that you see here with some stars and pluses. Here's one of the inconsistencies in the paper. In the paper he says, referring to this table on the right, that he's, to show the intensities of the spots that are present, he puts dots there. Well, there are no dots in table 1. You've got stars and plus signs. It's difficult to know what those mean, because it doesn't explain it. So he's obviously in a hurry to get this thing published. He's not paying enough attention to the details. So you can't really understand what that diagram on the right is. So then we see potassium chloride again on the left-hand side. And then from the Lowy type photograph on the right-hand side, we have sodium chloride, common salt. And he notices a difference. And at first sight, they look the same. But actually, there are missing points on here compared with potassium chloride. And it's this that starts him thinking, well, what is the difference between these two? And he realizes in the paper that the fundamental difference is potassium and chlorine have the same number of electrons. Now you have to remember, this is the time when electrons only just been discovered, and the concept of the atomic number wasn't known. But he realized that from the point of view of the periodic table, these two elements are close by. And so the idea is that they scatter very, very similarly, so that when you go from potassium to chlorine, it looks like identical atoms. And so the left-hand diagram you would interpret as a primitive cubic structure, simple cubic structure, but the diagram on the right reveals to you that it cannot be, it must be a face-centered cubic structure instead, because sodium and chlorine are quite different. This is one of those standard problems we always set undergraduates in examinations. So you can see here, the young Bragg, really very smart guy. I mean, at this stage, just in science at that time, so little was known about these things. So the other thing was that he discovered it depends also on the thickness of the crystal, because these spots come from different wavelengths that are picked out of this continuum. But with very careful reasoning, Bragg was able to realize that actually there must be, in addition to the continuous radiation, there must be some extra scattering, much more intense, to explain this pattern properly. To interpret a Lowy pattern, even today, is difficult. But to do it then is immensely difficult. So again, you see this. This is potassium chloride again, down the threefold axis, or nearly the threefold axis, hasn't quite got it set properly. Let's just show you a typical photograph of his time on the right-hand side. So you're dealing with really difficult patterns. Notice the elliptical spots again, by the way, in the Lowy pattern. These crystals that they're using are probably very large, they're probably 1 centimetre or more across. We would never dream of using such large crystals today. Now, this was the next great advance, a very important advance. This was the invention of the ionization spectrometer that I mentioned to you before by W.H. Bragg, his father. built by his assistant C.H. Jenkinson when William Bragg was in Leeds, in the north of England. And there were several of these were made, and some of these still exist. Just to show you a few here, the Cavendish Laboratories Museum in Cambridge is one, the Royal Institution has one, the Science Museum in London has one in Edinburgh. There's about 6 in existence. And here you can see Lawrence Bragg with a spectrometer, and over here it's about to make out Lawrence Bragg, William Henry Bragg, with this particular spectrometer when he was at University College London. And the difference here was that rather than getting these photographs which had these patterns of spots, they could actually now make measurements, because they could now put a crystal on there and scan, they could rotate the crystal and scan the crystal, scan the detector through it. The experiments are very tricky because X-rays were not very stable at the time, and there were lots of electrical problems they had to solve. This on the left is just again from the Bragg's paper, and you can see some of the traces of peaks that they got there, the realization that you could actually get the main intensities from what we call the characteristic radiation. On the right-hand side, he's actually made some calculations, and you probably can't see it, but potassium chloride, he calculates the volume times the density over the molecular weight divided by lambda cubed. They didn't know what the wavelength was, and he finds that he gets half the value for potassium chloride and sodium chloride. And then you see this diagram for the first time. This is the structure of sodium chloride appearing for the very first time. Now, I'll just finish one thing, or two things, just if I may say. The discovery was very, very controversial. The chemists didn't like this. They wanted molecules, not equally spaced atoms. Arthur Smithers, professor of chemistry at Leeds, said to Lawrence Bragg, please make the chlorine atoms a little closer to the sodium. And there's this very famous letter from Professor Armstrong, latest 1927. I'll just read a little bit of it. It says, Professor Bragg asserts that in sodium chloride there appear to be no molecules represented by sodium chloride. The equality of number of sodium and chlorine atoms is arrived at by a chessboard pattern of these atoms. It is a result of geometry and not of a pairing of the atoms. This statement is far more repugnant to common sense. It is absurd to the nth degree, not chemical cricket. Chemistry is neither chess nor geometry, and so on. And you can read that paper in Nature. And finally, even before these experiments were done, back in the 1890s, there was a rather odd gentleman called William Barlow, an amateur, one of the last of the amateur Victorian scientists, had no qualifications really, son of a surveyor who got interested in crystals. He discovered the 230 spacecrypts, and this paper in the middle in 1882 is where Barlow is speculating what happens when you take spherical particle atoms and you put them together in different arrangements, and particularly, for example, sodium chloride, and you'll see he has this alternating arrangement depicted here for the alkali halides, just by thinking about contacts. Barlow, amateur scientist, was made a fellow of the Royal Society. But there's another curiosity, just to finish with. There's another odd gentleman in Edinburgh, Alexander Crumb Brown. And he left behind a model, which is on the right-hand side here. As you can see in the Chemistry Museum in Edinburgh, it consists of balls of wool, red and blue, arranged on an alternative array, just like the structure of sodium chloride. We don't know why he left it there. We don't know what the purpose of this model was. But the interesting thing is, it is dated 1882, the same year as William Barlow's paper. And so it's possible that the two of them were in contact in some way. So here we are, the model of sodium chloride before X-rays were discovered. These ideas already were around. And Bragg in Cambridge was already in touch with Barlow. So when he was doing that paper, he knew about these models, and that was in his mind, and that's what enabled him to think in that way and come up with the correct structure. And that's how you get a Nobel Prize. Thank you.
You know, Mike, your lecture brings out very beautiful and often obscure ways in which scientific thought develops, and various streams of understanding that seem to sometimes not even be there together, but the way they come in and how suddenly you get the breakthrough thing. And yes, even as I was thinking about it, you were answering my question. I was wondering if they know about atomic number in those days. And no, they didn't know. And the so-called textbook question of KCl and NaCl, yes, I mean, idea of the they knew atomic weights, but that doesn't really mean anything. And they didn't even know that X-rays were, waves or particles even correctly. So to deduce the difference between the KCl Laue pattern and the NaCl Laue pattern is really nothing short of astounding. I mean, one has to sometimes put oneself in that era and looking at the kind of, and I believe that this is the sort of thing that one should try to communicate to students. Because too often in these days I find that people are just interested in passing exams and some kind of a bookish knowledge, trying to score more, and the higher you get in these exams, then you are considered to be worthy of getting admission into so-called better and better places. But all that this is the essence. So when you hear the story of the Braggs and how this 22-year-old literally boy was able to, yes, Bragg could correctly call his son my boy. How he could actually do this is nothing short of astounding. That's the sentiments that was evoked. Any comments, please? I'm sorry that I made the first comment myself. Yes, please.
So you mentioned all these inconsistencies, and it seems like everybody is voicing their opinions by sending letters to and back from Nature. In these days, what was the peer review process?
In those days?
Yeah.
Virtually none, as far as I can tell. Actually, in Nature, that persisted right up to my time. My first two papers were in Nature. I went straight through it. Those were the days.
Those were the days.
Those. If I may say something about the atomic number, there, because the Braggs were involved there, it was Henry Moseley that essentially proved the existence of the atomic number. Now, W.H. Bragg had published a paper much earlier in which he had found that link to Henry Moseley, but not in terms of atomic number, but in terms of atomic weight. So he got the kind of relation that Moseley found wasn't correct, because it isn't atomic weight, but that's proposed in the paper, the square root relationship to the frequency. When Moseley started his work, it was Rutherford that persuaded W.H. Bragg to let Moseley do the work, and that W.H. Bragg should work on crystallography with the sun. He was reluctant to do it at first, but he gave way. W.H. Bragg then invited Moseley to his lab to show him how to do those experiments. So that Moseley then was the person who got the correct results. Unfortunately for Moseley, he was killed in 1915 during the First World War, so he never got his Nobel Prize. And by the way, W.H. Bragg's son, Robert, brother of Lawrence Bragg, was killed in the same battle in 1915.
And which is why W.H. Bragg did not go to accept his Nobel Prize, because he said he would never set foot in Germany.
Now, what he said was, there will be German
scientists.
That's what he said.
There will be German scientists there, and therefore he never picked up his.
Which is very unusual with W.H. Bragg, because W.H. Bragg never expressed this feeling. That's the only time I know of it that he expressed it.
Yeah. One of the things which was intriguing for a long time was why Laue used copper sulfate crystals.
Can you speak louder? So
I heard.
No, the audience should hear the question. Why did Laue use copper sulfate?
But you just said that maybe because of the secondary, function, but I was not very clear.
He had his idea that the X-rays coming in will then get absorbed by an atom and then re-radiated as fluorescence. And if you're going to have fluorescence, copper is a natural thing to use. That's also why they use zinc sulfide for the same reason. But Laue should have realized something else, because Friedrich Knipling at the same time showed you 3 papers. The third paper in that list, appearing almost at the same time as the sodium chloride paper, is a paper by W.H. Bragg and W. of diamond. And that's the first structure of diamond, which is the same as silicon and germanium. Even more important than sodium chloride from the point of view of science. We depend on computing. And you know, in 1913 and 1914 until the First World War, the two Braggs had the whole field to themselves. And they have published loads and loads of papers, lots and lots of attempts at structures. They had the whole world to themselves. Unique experience.
In a lighter vein, before I close this particular talk, I asked the same question that Professor Ramanan asked to, I forget his name, to a person in the Deutsches Museum in Munich. We remember when we went for the German Crystallographic Association meeting, when they showed us the equipment. I said, was a senior German scientist, mineralogist, why did Lowy take copper sulfate? He said, no, for no reason at all. That's the only crystal they had in the lab that they could get in the hurry.
That's also true.
Yes. So we don't really know, and like in science, we don't really know the reasons for many things. Okay, let's thank Mike again. It's a pleasure for me to introduce the next speaker, Artem Oganov, who is a great science communicator. He works in both the USA and in Russia. And I had suggested to him that he speaks about the great importance of the NaCl structure in the context of quantum-state chemistry. And I was almost thinking that we missed you because we are registered and we weren't in the hall when we came. But here's Artem himself. And why is this structure the most common one for index structures? What makes it so versatile? Why is it still a topic of research interest? More than a century, yes. So, sodium chloride, he has done some outstanding contemporary work on non-stoichiometric sodium chlorides. So that it is out of the simple structure, you see, the simplest and most beautiful things keep yielding scientific results again and again and again. You never stop with sodium chloride. And Artem, I have great pleasure in asking you to come to the stage and give your lecture, please.
Thank you very much. And also happy birthday.
Oh yes, yesterday it was, yes.
It's a great honor to be invited to give this lecture, and this lecture, preparation of this lecture actually was quite an experience for me, because I thought about all the historical issues of our science, all the latest discoveries of our science, through the prism of this simplest and really the most widely known crystal structure. So I will start my presentation back in the 17th century. Already from the very beginning of the presentation, you will see every single issue that I will raise echoes in most modern research. And I will finish with the things which were discovered, partly understood, this year. Okay. Salt of the earth. Well, that phrase appeared actually even before the 17th century. That's the Gospel of Matthew. And I write here it in ancient Greek. Unfortunately, I cannot read ancient Greek. And in one of the English translations. You are the salt of the earth. But if the salt loses flavor, what is it good for? It's good only to be thrown away and trodden upon. That's from my memory. 17th century. The first crystal structure that people imagined was not sodium chloride of Barlow, but actually even before. Kepler was the first person, as far as I know, who drew the first crystal structure model. In his famous treatise on the six-volt star crystals of ice, he hypothesized that spherical particles can be laid into hexagonal motifs. And these would correspond to the structure of ice. Well, what Kepler actually drew, we now know not to be the structure of ice, but the structure of close packings. Structure of ice can be described in terms of close packings, but it actually itself is not a close packing. By the way, structure of sodium chloride is also describable, also based on close packing. Well, I think, given that this was pure speculation, pure imagination of a great scientist, this was a remarkable result for the beginning of the 17th century. But Kepler went even one step further, one giant step further, and formulated in those that time's terms what is now known as the famous Kepler's hypothesis. Kepler's hypothesis says that the highest density of packing of spheres in space is achieved by cubic close packing, which is the basis of sodium chloride, or hexagonal close packing, which is the basis actually of the ice structure and many other structures. Kepler's hypothesis was actually very useful for that time because British Navy actually at that time was given something like research grants for mathematicians to figure out the densest packing of spheres in space. Why? To pack cannonballs on board of British Navy's ships. Kepler was actually corresponding with people who were involved in this kind of research. And Kepler himself could not prove his hypothesis. His hypothesis was proven 2 years ago. Mathematicians tried to solve it for more than 400 years and proved it eventually only in 2015. An intermediate proof restricted to periodic structures was obtained by great Gauss, but the full proof, including also aperiodic structures, came only 2 years ago. And I think it is remarkable that what this great man has proposed was the first crystal structure model, idea of close packings, and this famous Kepler's hypothesis, which plays a big role in science, which was proven only 400 something years later. But really, as we know, the first crystal structures were solved by Braggs. That was the scientific experimental method. Diamond, zinc blende, rock salt structures were the ones solved for the first time. Mike has already shown a number of historical excerpts from the works of Braggs. I will indulge in showing a few more. First paper on crystal structure, the structure of the diamond, published in Nature. I wish I could publish such papers in Nature. Just 3 paragraphs, no pictures, no formula, no experimental data. Just a description which I think to a normal person is not really very intelligible. You put a cube, in the cube you put some atoms here and here, every atom has 4 identical neighbors, and I think zinc blende has the same type of structure, except that you need to color atoms in 2 different types. That is roughly the content of that paper. Amazing. I wish we could do it these days. And then the same paper as Mike has quoted, where for the first time equations and crystal structure drawings appear, and the structure of sodium chloride is discussed in greater depth. You know, we think of Bragg's achievement as great triumph. Really, 2 years after their first publication, they got a Nobel Prize. Bragg, the son, William Lawrence Bragg, is the youngest ever Nobel laureate in physics. And I think there was nobody younger than him in chemistry or biology either. So in all the good Nobel Prizes, except, I don't know, maybe for peace they give younger Nobel Prizes, but in hard sciences, the youngest Nobel Prize winner. But actually, we overlook the great conflict that was underneath. And Mike already mentioned that a wonderful letter of Henry Armstrong. And Henry Armstrong was no small fish. He was a fellow of the Royal Society. 15 years after the discoveries of Bragg, he was able to write this letter in Nature, and just a few quotes. I think it's extremely rude, this letter. Repugnant to common sense, absurd to nth degree. Chemistry is neither chess nor geometry, whatever X-ray physics may be. Against worship of false gods. So he calls either X-ray diffraction or Bragg's false gods, worshipped by some not very intelligent people. Remarkable. Well, X-ray diffraction, we know the basis. Atoms have similar sizes to the wavelength of X-ray. There will be reflection. Reflection can be described as reflection in a very simple model from atomic planes. Bragg also figured out physics, mathematics of this process, writing these equations using complex numbers, which I think was also quite remarkable for the time. And well, that is the basis of what we know, what we use until now. This method, this great method, has been basis of a huge number of Nobel Prizes. At least 26 Nobel Prizes can be counted using X-ray diffraction. In fact, it was in the laboratory of William Lawrence Bragg that the double helix structure of the DNA was solved. And in fact, Bragg's name is not on the paper. So he had enough decency and modesty and appreciation for his younger colleagues not to insist on being put on that paper. You can see here X-ray diffraction from the DNA molecule and, well, this famous model from the very first publication of Watson and Crick. Okay, that was a brief introduction. Now let me tell you a little bit more about rock salt and its friends, analogs, derivatives, and a little bit about theory of sodium chloride and how it has changed modern science. This is rock salt structure, chessboard, three-dimensional chessboard. These are the minerals that belong to the rock salt structure and some synthetic compounds which are not formed in natural environments but can be easily formed in the laboratory. To this structure type, to the rock salt structure type, belong ionic materials, metallic materials, semiconducting materials. Huge variety of compounds choose this structure. Sometimes rock salt type materials can be fully stoichiometric. That means one atom of A type corresponds to exactly one type or one atom of B type in the chemical formula. But sometimes it would be non-stoichiometry. Sometimes the metal position would be depleted of atoms, such as iron oxide. By the way, this corresponds to coexistence of 2+ and 3+ iron and is responsible for catalytic properties of this interesting mineral. Stoichiometric FeO is unstable. Sometimes it is the non-metal atoms which would be depleted, such as in nitrides, in carbides, and so on. And physical properties depend very strongly on the exact content of metal and non-metal in the structure. So actually, if you can vary this metal, non-metal content, you can tailor your material to have the properties that you want. You can actually change the properties of your material in rather wide ranges. By the way, here I show one of the sodium chloride type materials which displays this kind of non-stoichiometry. It's titanium nitride. Titanium nitride has a beautiful golden color and actually is often the coating on, for example, churches. When you think a church has a golden cupola, well, it's not gold, it's titanium nitride. And often titanium nitride would be used as a hard coating for machining tools, such as this wonderful screw coated with titanium nitride, and you can clearly see the golden color. Okay, so here we begin to encounter a lot of complexity, and people are still studying in great depth these non-stoichiometric sodium chloride type materials like wüstite, iron oxide. A lot can be done. Many derivative materials, many derivative structures can be invented. For example, if you replace the non-metal atom, the chlorine, if you replace it with a diatomic group, for example, 2 sulfur atoms, you would get pyrite structure type or calcium carbide structure type. Pyrite is known as fool's gold. It has golden color, and many beginning amateur people driven by gold rush to the west side of America were badly mistaken and badly fooled by picking up this abundant mineral and thinking it's gold. And calcium carbide is a material of my childhood, because in my country, in the Soviet Union, there were a lot of construction sites where they would scatter, I don't know why they would scatter these huge amounts of calcium carbide, and we as children would come to the construction sites, steal these pieces of calcium carbide and throw them in water, and it would emit acetylene, which you could burn at some risk to yourself. Here is the structure which was discovered only a few years ago by our group, and actually Carlo Gatti, sitting here, was a co-author on that paper. If you replace metal atoms with boron-boron pairs and non-metal atoms with boron-12 icosahedra, you get a complicated structure of gamma boron. And gamma boron is one of 5 hardest substances known to humans today. So it's a wonderful super hard material formed at elevated pressures, but it can also be considered as a rock salt type material. And the latest discovery, which we just submitted to a journal, it has not been published, but it is very fascinating in my opinion, is the discovery of a new high-temperature superconductor, which also has a structure based on rock salt. If you replace the non-metal atom, chlorine, with a cubic group of 8 hydrogen atoms, and on the metal sides put uranium, you will arrive at the material whose formula is uranium H8. And uranium H8 is stable at conditions of elevated pressure above 50 gigapascals or 500,000 atmospheres. It can be decompressed to lower pressures. It can still exist if you decrease the pressure, and it displays temperatures of temperatures of superconductivity of almost 200 degrees Kelvin. Previous record was 135 degrees Kelvin. Recently, there was another record of 200 Kelvin set. And here you have the same kind of superconductivity, extremely high temperature, approaching room temperature, but at lower pressure. So that's a wonderful material. And there are already some preliminary experimental attempts to synthesize this material, and the attempts seem to be successful. Why and when sodium chloride type structure would be formed? Well, Linus Pauling, another genius scientist, when he was only 26 years old, formulated 5 famous rules which dictate structures stable for ionic compounds. Sodium chloride perfectly fits these rules, but other materials do not always do. The first Pauling's rule, for example, says that cation and anion distance is determined by the sum of the radii of the atoms, and the coordination number, meaning the number of neighbors around this atom, is determined by the ratio of metal to non-metal atoms. The bigger the metal, the more neighbors it will have, the higher coordination number. We can see that the first part of this rule is fulfilled very well. Indeed, the distances between the atoms are determined by the sum of the radii, quite accurately. Here you see predictions and observed distances. But coordination numbers do not always follow this trend of being determined by the ratio of the ionic radii. So the first Pauling's rule is working often, but not all the time. And it is important to remember that concepts of crystal chemistry are approximate and are more guidelines than rigorous quantitative tools. Now let us talk a little bit about theory of sodium chloride. Let us talk about chemical bonding. Chemical bonding is believed to be ionic. That means that sodium atoms give away their only valence electron, and chlorine atoms take that electron. So you have positively charged sodium and negatively charged chlorine. They interact, they attract each other, and this stabilizes the structure of sodium chloride. The concept is very simple. That's the simplest concept really you can make for chemical bonding. It works quite well, but even for this simple concept, there are interesting consequences. First of all, within this concept, you can expect only one-to-one NaCl compound. For example, Na2Cl formula would be forbidden. You can write the energy of interaction of two atoms as a sum of electrostatic attraction of sodium and chlorine and short-range repulsion, because atoms have a certain size and they don't want to overlap with each other. So overlap of electronic shells would lead to some short-range repulsion. You can write mathematical formulae, and if you differentiate the energy, you will be able to obtain many, many physical properties. For example, compressibility is determined by the second derivative, by the curvature of this energy well. One would think that this is very simple, but actually you immediately encounter tough problems. One of the problems is that the Coulomb interaction energy of interacting charges, is very, very long range. So if you try to sum all the interactions within the crystal, your sum seemingly will never converge. Different terms which you encounter at different distances will oscillate like crazy, and in fact, the magnitude of oscillation will only increase with distance. So how come sodium chloride has a definite energy if the sum never converges? Actually, Peter Ewald was the one who was able to figure out the solution. In fact, the sum converges, but to get the converged solution, you need to play a trick. You need to split this sum into two sums, one of which converges fast in real space, and the other one converges in reciprocal space, a concept which was at about that time invented by solid-state physicists and crystallographers. And Abel method is widely used not just for calculating the energy of sodium chloride, but also for simulations of plasmas and galaxies. So you can see how one field immediately impacts completely different fields. Predictions of this ionic model correspond to experiment quite well. You can see, for example, the cohesive energy of different sodium chloride type structures. You can even calculate complicated properties, such as absorption or reflection spectra, infrared absorption and reflection spectra of crystals. And these numbers and graphs I have taken from another milestone book of Max Born and Kung Huang, 1954 masterpiece called Dynamical Theory of Crystal Lattices. And Max Born actually also got a Nobel Prize. So you can see how one great discovery impacts another great discovery. Everything seems to be okay if you consider sodium chloride as an ion within the ionic model. But if you begin to look at details, the picture becomes a little bit more complicated and gradually falls apart. If you look at the elastic constants, and elastic constants characterize the ability of the material to deform in different directions, then you will be able to formulate the so-called Cauchy's law. Cauchy's law puts a strict equality between two elastic constants for cubic crystals where all the atoms have centrosymmetric environments, like rock salt. So for rock salt, two elastic constants, 1, 2, and 4, 4, must be identically equal to each other. When you look at experimental data, you find that for sodium chloride they are close but not equivalent, not identical. And if you go to crystals like magnesium oxide, which also has the same structure, the difference is huge. The difference is actually enormous. And you can never reconcile it with a simple ionic model. You can reproduce it, however, if you do sophisticated quantum mechanical calculations. So why does this ionic model break down? Because it assumes that energy is pairwise. If we talk about interactions within this room, my interaction with Mike, my interaction with the next gentleman, and all the pairs, if you sum up all these interactions, they would make the total interaction energy within this room. But this never works like that. Even in human society, there is a complicating effect named many-body interactions. The simplest many-body interaction is a love triangle. John loves Leslie, but Leslie loves Michael. Do you think this will affect interaction between Michael and John? Of course. Their properties have now changed through the interaction with the lady. Love triangle, many-body interaction. In this case, 3-body interaction. But there are also 4-body interactions and 5-body interactions and n-body interactions. And in general, you cannot ignore them. And in this case, magnesium oxide shows particularly strong many-body interactions because oxide ion is unstable. It depends completely on its environments. It's stabilized by the environment. So if you put its neighbor further away or closer away, the properties of the ion will change dramatically. Many-body interactions at work. Properties of atoms are not constants. Interaction of one atom with another depends not only on these atoms, but also on all the other atoms around. Many-body interactions exist. And unfortunately, it's very difficult to describe them, and we still do not have a consistent analytical theory of many-body interactions. But now, a very popular direction of research is related to artificial intelligence and machine learning. Machine learning would take different arrangements of atoms, energies corresponding to them, and figure out a model, a black box model, which would be able to predict interactions for any other positions of the atoms, taking into account also these complicated many-body interactions. In modern science, whatever you cannot describe neatly, smartly, by pencil and paper with equations, can be described and even predicted by machine learning. Machine learning takes care of human ignorance. So this way we can get perfect accuracy, and in fact we can recover well-known Lennard-Jones type energy interactions between noble gas atoms, well-known oscillatory interactions between metal atoms in aluminum, for example. All of the things which classical theory has figured out, we can find with machine learning. And in addition to that, these complicated many-body interactions can be taken into account. And now look at how well this machine learning works. Just a few days ago, we published a paper where we computed melting temperature of aluminum. From machine learning, it's 925 Kelvin. From quantum calculations, 912. Perfect agreement. An experiment is very close to that too. Why do I show you aluminum and not sodium chloride? Because sodium chloride right now is extremely difficult to be described even by machine learning. Machine learning has not yet quite come to that stage of describing sodium chloride. For some problems, sodium chloride is still too tough. Do I have a couple of minutes? Okay, let me just show you a few results that have been obtained. Sodium chloride was thought to be so well understood and so simple. But now we know that sodium chloride is not just NaCl, that there are new compounds made of sodium and chlorine, forbidden by simple ionic model, but allowed by quantum mechanics and proven by experiment. Here is the phase diagram, which shows pressure ranges of existence of different compounds. You can see such compounds as NaCl7, NaCl3, Na4Cl3, Na3Cl2, Na2Cl, Na3Cl. An experiment has already synthesized and proven the existence of such compounds. Crystal structure prediction goes even further. And for example, recently we published a paper in Nature Chemistry where we predicted, theoretically and experimentally confirmed, that under pressure, helium is not so inert as we thought. Helium is the second most abundant element in the universe. And we thought that it has no chemistry. It cannot be ionized, it cannot attract electrons from other elements, it cannot share electrons with other elements. Nevertheless, under pressure, it forms this beautiful fluoride type structure, material Na2He. And here you also have a chessboard type motif. It's a different chessboard of cubes. And this structure also can be described on the basis of close packings. And let me now give you again this slide, and that will be the last slide of my talk. A sodium chloride type structure of new material, uranium H8, which promises to be, which is predicted to be one of the most interesting high temperature superconductors. This prediction was made just a few weeks ago and is awaiting experimental confirmation. So rock salt is really the test bed of new theories. Rock salt is a structure which is taken by many materials. Rock salt, in some senses, has been well understood, and in some senses is still a challenge for modern science. Thank you very much for your attention.
We're running short of time. I'm just going to pose a question to the audience based on what we've heard. Professor Armstrong were to come back today and see the paper on non-stoichiometric sodium chloride, would he call chemistry as chess or geometry or both or neither? So I think this once again shows that, the sodium chloride is always the same. I'm coming back to Aristotle and the holistic model. And the form is always there, and the way in which you think about it, the substance, the properties, everything, they come and go out. That is not so important. It is the form itself, and I think this is coming through all. Thank you, Artem.
Thank you.
Questions to Artem, please address them after the thing, because we're already running short of time. But I'm not going to deny or deprive time for the speakers. A great pleasure to call Anita Das. Now, I told you all the talks in this symposium were going to be different. And what about sodium chloride and money? Sodium chloride and industry. It's not just salt that we eat. The very first quotation of Artem on salt was it when you said that when you remove the salt, you can throw it and walk on it. There are other things you can do with sodium chloride other than eat it. And Amitabha is the director of an important government lab which is devoted to study of salt and marine research chemicals. Bhavnagar in Western India, not very far from Dandi, where Gandhi did the march actually. And he will provide a glimpse about the importance of extracting potash fertilizer. So again, sodium chloride, potassium chloride dichotomy. So sodium potassium balance is not only to do with
Cassie Technical School. After that,
Let me first thank you. It's a great privilege to be here, to be sharing the data. And all of you have mentioned that sodium chloride, the chemistry, science lies with, understanding the sodium chloride. But sodium chloride also has a huge presence in chemical industry. So I'm trying to give a very glimpses of this presence of or importance of sodium chloride in chemical industry. And thanks to Mr. President and our organizing committee of this IUCR for giving the opportunity to be here and sharing some of my experience or working with I belongs to an institute which is greatly known for this contribution in the area of salt. And my first slide is actually made my life easy is Dr. Dinakar Joshi. He already mentioned you about that Dundee March. You know that first one of the major strategic. I have if I would like to stress this the word strategic importance, and this could not be even more than strategic than this the Dundee March, where the first civil disobedience movement was initiated to making of the salt. So, and if you know that I will start with a statement made by Mark Ernstly very recently in his book Salt in World History. It has been mentioned that salt is so common, so easy to obtain, and so inexpensive that we have forgotten that from the beginning of the civilization until about 100 years ago, salt was one of the most sought after commodities in human history. Salt, if you go to talk to anybody, salt doesn't mean anything. It's so cheap. But around 200, 300 BC, salt, salary was paid in terms of salt. And the word salt came from the word salarium, Latin word salarium. So, and there's a very saying, old saying is that worth your salt. So salt is actually a very, very important commodity in our everyday life. Now, let us come back to what is the importance, how the salt industry in India, it evolves. It started importing salt, India as a country, in the 18th century. I will not go into the details about the, how it is taxed and other things. In 1944, the first organized salt production started in Okha. This is a place in Gujarat by Tata Chemicals. And 1949, the first soda ash plant started by Tata Group. Why I mention this soda ash and sodium hydroxide and sodium carbonate? These are the two major chemicals which has driven the importance of sodium chloride in usage of sodium chloride in chemical industry. So I have a special mention of this one. As my talks goes on, I will be talking a little bit about how this sodium chloride, sodium hydroxide and sodium carbonate has driven that demand of sodium chloride in today's chemical industry. In 1947, salt was being imported from the United Kingdom, and India, at this present status, India is the third largest salt producing country in the world after China and USA. And at present, India's India produces about 270 million tons. And in 1947, it was 1.9 million tons. So you can see there is a huge growth in terms of salt production of this country. Now, sources of salt in this country basically, or anywhere in this world, is a sea brine, lake brine, subsoil brine, or the rock salt deposit. Now, as far as the India is concerned, marine salt works, basically it comes from Gujarat. You need to have a coastal area. So Gujarat, Tamil Nadu, Andhra Pradesh, these are the major salt producing states in India. And these three states produces about 96% of the salt this country produces. And Gujarat itself produces 75% of the salt that this country produces. And there are reasons, I will come to that point. And inland salt means this is a lake brine or the subsoil brine. And that is the Rajasthan, it contributes hugely, about 20-25% of the salt production of this country. Sorry, 16% of the salt production of this country. And other salt works like Rann of Kutch, there's a unique, biodiversity we have. They also have a subsoil brine. There from also we can produce salt. And the rock salt deposit, there's a minor rock salt deposit in Mandi. So these are the, the sources of salt in this country as far as India is concerned. Now, this is very important. This slide is very important to understand the complex Indian industry as per the sodium chloride is concerned. Salt manufacturer engaged in India at this present is a common salt is about 11,800 people. Area covered for salt production is 24,000 square kilometer. Mostly is a coastal. 86% of the salt manufacturer are small salt producer. This is very, very significant. And 6.6 is a medium scale producer. So altogether, they contribute 38%. That means close to 40% of the salt, this industrially important salt, this country produces comes from either the small scale producers or the medium scale producers. And the large scale producers is a 5.8%, people like Tatas, Birla, Grasim, all the major industries, they are in the salt production. They contribute about 62% of the salt. And this is very important if you want to address the Indian population, who are involved out of this population, who are involved in this salt producing of the salt, industrially important salts. Now, as I mentioned, Gujarat produces 76% of the salt this country produces, sodium chloride. Salt means I commonly refer as sodium chloride. Tamil Nadu 16%, Rajasthan 9.8%. Together 96%. All other states, they contribute only 4% of this. The average supplies of salt, the human consumption, we have a common understanding that salt means it comes only for the edible salt. That is only the 35% of the total consumption, and 60% of the salt this country produces goes for the industrial production. So it clearly shows that salt we produce has a huge industrial application. Now, that's what I mentioned. This is important if you want to understand the Indian salt industry. There's other point which is crucial for the policy making in Indian salt industry is that 40% of the road, edible salt moves by road, and 60% moves by rail, by trains. And 88% of the industrial consumption, that sodium chloride, that's a major consumption, that is transported through road. So that is very strategic, why we should have a salt works. If there is a chlor-alkali industries, your sodium chloride production somewhere has to be close to that if you want to reduce the carbon footprint at today's context, if you want to reduce that pollution environment. So this is just the figures, facts and figures. It shows that Gujarat is the highest producing of salt, then Rajasthan, and then Tamil Nadu. This is again the facts and figures. It is from the Government of India website. Salt produces, edible salt is 6.06 million metric tons. Industrial salt is 11.5 million metric tons. We are exporting about 6.5 metric million tons. So total is about 24 metric million tons. Now, salt is a basic raw material for caustic soda, as I mentioned, and caustic soda ash industry. 37% of the total salt produce is being consumed by the chlor-alkali industries. So now you understand which is the major consumption of the salt, and that is driving that, the salt production in this country. Salt production means, I am coming to this point, salt production means I am coming to the point of salt purity of 99.5%, which is essential for the chlor-alkali industries. And that also in a pan is not for in a lab, it is in a thousands of acres, thousands of kilometers span. You have to get it that purity, 99.55% purity, or more than that in an open solar evaporation pan. Growth of chlor-alkali industry is 5 to 6% in the past 5 years. And the current year requirement of the salt will be 12 million tons for the chlor-alkali industries. So the main consumer of salt. So chlor-alkali as well as the soda ash industry, these are the two major industries that is driving the production of the sodium chloride in this country or globally. Now, this clearly shows the economics. As the purity goes up, the price goes up. And you can see that very steep increase in the price as you go on the purity. What are the other common impurities that calcium sulfate is? You know that seawater can have, or the subsoil brine can have, magnesium chloride, calcium chloride. Everything has to be removed. And you have to attain a purity, and these have to be in the ppm levels, this calcium and magnesium, to get the salt, sodium chloride, which can be used for the chloralkali industries. So, any impurity, the reason is any added impurity here or higher concentration of this means this salt has to be treated before you can use it for the chloralkali industries, and that pushes the price up. So I will skip this one. This is basically it clearly shows that chloralkali industries is a very simplistic presentation. You need basically the pure sodium chloride and just the electrolysis for this one. Now, caustic soda production in India. That again I am telling, these are the two major, which is driving the production of sodium chloride in this country. Now caustic soda, if you see this one, production is going up at the rate of 4 to 5%. If you see this, demand is much more than what you produces. So there is a gap. There is a gap, and this gap can only be filled up if we can have a production to meet the demand with the desired purity of 99.5%. And as I mentioned, 5.5% salt that salt producers are from the major players. There is a big industrial houses in India: Aditya Birla, Gujarat Alkali, DSCL, Reliance Industries, Tata Chemicals, everybody. In them, any big industrial houses here, they are in the business of sodium hydroxide preparation. And this is sodium hydroxide is being used in all sorts of industries. So this is just to give an overall idea how sodium hydroxide and sodium soda ash industry are so relevant for our industrial growth, as far as the chemical industry is concerned. Now, expected growth, as I mentioned, sodium hydroxide growth rate, industrial demand is 5 to 6%. And if you look at this, sodium chloride growth rate is 3 to 4%. So we are still lagging behind. So the demand is more. That's what I repeatedly telling. Demand is more, and we need to enhance our capacity for producing sodium chloride. And if this is a global scenario, as far as sodium chloride is concerned, and the growth rate, as you can see, in the Asia Pacific region, is much higher as compared to Europe and America at this moment. And this is primarily driven by the two major countries. One is India and China. So this is basically the graphical presentation. As you can see, the same facts and figures if you put in the graphs. This is the Asia Pacific region. You can see the growth is maximum here. This is a different time zone, 2008, 2013, and this is predicted at 2018 demand. Okay, and this is the Indian scenario, how it is the sodium chloride production is going up, and this small one is the percentage of increase. So I'm trying to give you an idea that sodium chloride is one of the major production in, one of the major component in as far as the chemical industry is concerned. This graph is showing what are the overall distribution of the sodium chloride, or salt works in the different parts of the India. I'll come to this point. Who produces 76.6% of the salt that country produces? Gujarat. These are, you can see, these are all basically the coastal area. You can see exactly everything are distributed in the coastal area where it produces the, the 76.76% of the sodium chloride. And apart from that, there is an area called Greater Rann of Kutch and lower Little Rann of Kutch, GRK and LRK. They also produce salt from the subsoil brine. Now, these are the ports. I'll skip this one. These are ports which are basically involved in the salt production. Now, as I mentioned, achieving 99.5% purity in the solar pan is not easy. So there are several steps one has to take in the open salt pans to get this, remove this calcium and magnesium, and that has to be. So it is, while I'm telling, I'm not a salt chemist or not a technologist. Is all the work I'm going to talk about here is all done by my colleagues. So I'm going to talk about what my institute is associated with. This is an adjacent area where our institute has a few hundred kilometers away of the span of the solar salt pan. This area just adjacent to this, our solar salt pan. What I'm trying to show you, there's migratory birds, flamingos in the month of April in 2017. Now, this is typically how the solar salt pan looks like. This is the initial sedimentation or the clarification happens. Then the gypsum recovery happens here, and gypsum goes to the industry of the main consumer of the gypsum is the cement industries. And then it comes to the pre-crystallization. There we can take care of that calcium and magnesium a little bit. Calcium has gone out here. Some magnesium can be recovered here. But this is this is a crystallization of the pure sodium chloride, and where we have to achieve 99.5%, which can be used only for the chemical industry, chloralkali industries. Then it comes to the stage where after recovering of the sodium chloride, it comes to the liquid. It is called, the reservoir is called the bittern. The bittern, that word comes from, once you remove the sodium chloride from water, seawater, it will taste bitter in the tongue. So it is called a bittern, and that is a source. That is a potassium content is about 1%, 1, 1.2, 0.9, depends upon the variation of the source or the areas. And that is a source for potash, and that is a technology available for developing or recovering potash commercially viable way from this bittern. And there is again the liquid left out can be used for the magnesium recovery. So this is basically the chemicals that can be recovered from through seawater evaporation. So these are our interest is on crystallization of the sodium chloride and the potash that you can recover from here. Now, apparently it is very simple. Just evaporate sodium chloride on an open salt field, and you can get the sodium chloride. But there are some science goes on behind it. Even the depth, what you charge the salt pan, that also adds to the quality of the solid crystal you isolate. If with the depth, you can maintain a depth of certain height, you can improve the surface area of the evaporation. And in that case, you will be left out with the solid crystals. And if the depth is shallow, you will be left out with a hollow crystal, which has a tendency to trap impurities in it. So every minor details is important to get the desired purity of the sodium chloride in the solar salt pan. Just to give you an example, these are the two areas. This is a Gujarat, okay, I have mentioned. This is a LRK, Lower Rann of Kutch, where the subsoil brine has been used for the generation of the production of the sodium chloride. Industrially important means 99.5% sodium chloride here, purity. Okay. And this is, I have taken another example, is a salt farm, which is in Bhavnagar, from which we belong to. Now, the sea brine and the subsoil brine in LRK is completely different. They have a difference in composition. Sea brine has a higher sulfate content, so separating calcium sulfate is much easier. Okay? If you go to a certain density during the evaporation, you can completely get rid of calcium sulfate before you start the crystallization of sodium chloride. But the moment you go to LRK, that sulfate content is less. So it is not easy to get that purity so easily. That is the interference area. So you have to treat with the sulfate, additionally, charge the sulfate additionally. And again, you cannot put too much charge too much sulfate. If it is there, again, you have to remove it at that end. So each variation, what I'm trying to tell you is that salt production apparently looks very simple, but technologically is not so simple. Now, these are the different, things I mentioned. The purity we need for the chloralkali is 99.5%. And if we achieve that then making sodium chloride 100% for the chloralkali industries, you have to spend about 3 US cent. That means equivalent to 2 Indian rupees per tons of salt, 1,000 kg of salt. Still, that is a treatment you need before you charge it for the chloralkali industries. Now, this institute, our Central Salt and Marine Chemicals Research Institute, we have a process to be implemented in any solar salt pans, small or large size, significant improvement in whiteness, salt suitable for chloralkali and soda ash industries, highly effective for removal of the trace impurities, where conventional crystallization would be cost effective and scalability would pose a problem. So we have a process or technologies which is scalable to at any levels. And all our processes are IPR protected and technology ready for transfer. So just to give an example, some of the examples, industrial grade solar salt. As I mentioned that India is the third behind China and USA. We export and now we are exporting salts also, and the demand for solar salt is increasing 4 to 5%. And by 2019 and 2020, India will be requiring 28.4 metric million tons. So we have to catch up still. And this apparently looks simple, but achieving that is not so simple. Now, CSIR-CSMCA has developed ultra pure salt, 99.5 and 99.8% purity sodium chloride for chloralkali industries. These are again, as I mentioned, are IPR protected, and our process is being licensed to Tata Chemicals, as you all know about the Tata, Grasim Industries, Tamil Nadu, DCM Tamil Nadu, then GSCL, Hindustan Lever. Recently we have demonstrated, and this is one of the demonstrations recently we have shown to Tata Chemicals, Hindustan Lever, Unilever Group. As I mentioned, 40% of the salt comes from the marginal salt workers are called agarias. So this is the examples, and it is very important that technology goes down to the root level to the agarias, so that they can produce a salt of that quality and they can improve their earning. The reason is, if the salt purity is 97%, that will fetch them 250 rupees or less than 250 rupees per 1 ton, means 1000 kg. If it is purity is 98.5%, that will fetch them 450 rupees a ton. If they can achieve 99.5%, that will fetch them 600 to 800 rupees per ton. So you can see this is almost 3 times. That adds to their livelihood. Okay? So it is very important that technology goes down to the grassroots. And our institute works with several NGOs in teaching them how to produce a good quality salt in any salt farms, and that can be marketed directly to all the major players. So technology not only for the big players, technology for the marginal players also. And this is an example why this is an example why I say this is a strategic importance of producing salt in Rajasthan. I will come to the next slide. I'll explain you. This is again from the subsoil brine. So far I have given an example from the sea evaporation. This is an example from the subsoil brine. Now there is a place in Rajasthan, Sambhar Lake. You all know there is it's a closed lake, and there is no outlet. And basically the river water comes and comes to that. All the rainwater comes and accumulated there, and it just gets evaporated. And in the process, the salinity goes up over the years. As the salinity, this lake is so saline, it can produce salt. Salinity is even more than sea water actually. So this water can be used for the generation of the salt of the sodium chloride in a commercially viable way. And we have recently demonstrated that you can achieve industrial grade 99.5% or higher on dry basis of sodium chloride from this salt. And this is recently we have shown and demonstrated, and recently we have taken a FTT project. It's called Fast Translational Project. It is showing the viability or repeatability of the process. Now, why it is strategic? I said that. Now, at this one, these are the dots. The green dots are basically the chloralkali industries, and the salt is being transported from this area, mostly from these areas to these places, these chloralkali industries. What does it mean? If we have a salt production here in Rajasthan, the salt transported here, I have given just one example. That will reduce the transportation. All are transported mostly by road. instead of almost 800 kilometers, it will reduce to 300 kilometers. So you can understand how we can bring down the cost of that salt available there to make it available there. Secondly, how it can reduce the carbon footprint and save the even the fuel too for this country as for the world. Now, I will move away from this a little bit. There is a, in India, there is not only in India, there is a global problem. The 30% of the world population suffer from iron deficiency. Okay. And India has a larger share. So, what could be the best way to produce? And most of these people who are deprived of this iron deficiency, who suffer from the iron deficiency, they are basically, how much time we have? 2 minutes. Okay. Okay. So, mostly the poor people. So, we have come up with a process of providing salt that is iron rich. What we have done, we have taken the sea bittern, and from the sea bittern, we have produced a hydrotalcite, basically a magnesium iron mixed oxide hydroxide, is a layer structure. And in the space, it got some iron is there in the system. And when it gets in the stomach, at a certain pH, it decomposes to release iron and gets absorbed. And our study shows that a bioavailability of this iron is much higher than the common iron being used for the common iron salt that is available in the market. And that has already passed all the food safety and security standards, and recently is undergoing this limited clinical trial as a part of the nutraceuticals, limited clinical trials for application. I'll skip this one. So just to give an example, I said only about the industrial application. Our institute also works on that science part, also on the understanding the salt growth and other thing. Typically, sodium chloride is a cubic structure. All of you have discussed so much. Now, how you can change the morphology of this one? The thing is, if you can add some additive, you can particularly block the one particular phase. The moment you block one particular growth in a particular phase, it grows the other phase, allows the other phase to grow, and you can change the morphology. So one of our colleagues, he has used a glycine as a modifier, habit modifier, and changed it from cubic to dodecahedron structure. The reason for this, dodecahedron has a much more better improved free flow character as compared to normal cubic structure. So this is just how we can change this morphology again, just by mechanically changing the starter starter configuration. This is an example how we can again change the morphology is by the trinucleoacetic acid as a habit modifier, and you can generate a perfectly dodecahedron structure instead of cubic. This is exactly what I mentioned. We particularly block this one phase and allow the 1,0 phase to grow, and it allows the molecule to get that crystal structure. And this is been demonstrated in the seawater and the subsoil brine. Again, and this is the last example how we have taken a barbituric acid. The reason is this one favors the octahedral structure, we know, and this part favors the dodecahedral structure. So we thought that, or my colleagues thought that he can combine both to generate a mixed structure. That's exactly he has done. When we come up with this one, at a certain pH, it favors that octahedral structure. At certain other pH, that means one reproduced form, it favors the dodecahedral structure. So what I want to tell you is that instead of cubic structure also, you can play with the habit modifier to get into the different morphology, different applications. All this were done with the requirement to some of the, our industrial application, some of the requests. So these are all for specialized application of sodium chloride. So I'll skip this potash. I don't have a time. So in conclusion, basically what I tried to tell you is the seawater, source of sodium chloride, improved quality of salt is basically driving that chemical industry of sodium hydroxide and sodium carbonate. Policies related to salt production are crucial for Indian economy. Sea bittern, source of MOP and SOP, sorry, I didn't talk about that. And this one I couldn't cover in my talk. And thanks to all of you for your kind patiently listening. Sorry, I have taken 1 minute.
part of the issue is geographical, because Gujarat happens to be at one geographical extremity of our country.
Yeah. Not only geography, it is also the the very high evaporative zone. That humidity is very low, so that also adds to that that faster evaporation, faster crop cycle.
Yes, very interesting indeed. And to see the various ramifications.
Yeah.
I was even thinking about other things. Now we are going away from sodium chloride. That this rail transport versus road transport is another serious
These are
issue.
these are related to the issues or strategy that this country needs to adopt.
It is addressing, because the road transport is so expensive that there's got to be some way of, each thing seems to be linked to the next one, and you can see how science just comes gently through the whole process. Thank you very much, Dr.
Thank you, sir.
Thank you. I would request all the speakers to please come up here for a